Let us start today. So today we are going outside our galaxy. So today is the day of cosmology. So two talks on large scale structure and a cluster of galaxies. And Arka will talk about neutrinos. So I think you phenomenologists will like neutrinos. So let us start what Arka has to say about large scale structure and neutrinos.
Okay, thank you, and thank you to the organizers for giving me this opportunity to talk. It's been a wonderful conference. Thank you. I'll be talking about the imprints of massive neutrinos on the large-scale structure of the universe. These are some of my collaborators involved in this project. And this is the basic outline of my talk. I will introduce various observables of large-scale structure, especially in the context of photometric surveys. Then I'll talk about how massive neutrinos affect these observables, in particular how they change the matter power spectrum and the prospects of measuring the neutrino mass using these observables. And finally, I will talk about this unique signature of massive neutrinos on cosmology, which has been explored in only the last 4 years or so. And that has to do with the spatial clustering of collapsed objects like halos or other nonlinear objects like voids. I'll explain all of these terms as I come to them. So this is a brief history of the universe in one slide. The central assumption is that the background universe is homogeneous and isotropic, and you need just one number to describe that, which is called the scale factor, represented by A here. The evolution of the scale factor is governed by the Friedmann equations, which are put down here, which relates the change of the scale factor with time to the energy density in the universe, belonging to different components, matter, something like cosmological constant, the curvature, and so on. So let me focus your attention to this picture here. The so-called standard model of cosmology says that you had, at very early times, you had a period of accelerated expansion which lasted long enough to stretch quantum fluctuations onto classical scales. That is called inflation. Once inflation is over, whatever field caused inflation, the inflaton, then transferred all of its energy to the particles that we see today. The background universe continues to expand and cool. The perturbations, the quantum perturbations now stretched out onto classical scales, evolve under gravity. As the universe cools, at some point the temperature is low enough for electrons and protons to combine into neutral hydrogen. And that's the era at which the CMB, or the cosmic microwave background radiation, is emitted. And the pattern that it has tells us a lot about cosmology. I'll come to that. As time evolves, okay, once the CMB is over, the universe is basically transparent to photons. So photons can travel all the way from the CMB surface to us sitting here. As the perturbations evolve, at some point, stars and galaxies start forming, okay? In the meanwhile, the background continues to expand. At some point, there is a second phase of accelerated expansion, which is where we are sitting right now, okay? If you look at the energy content of the universe today, it is made up mostly of things that we have very little clue of. So about 73% of the universe is made up of this mysterious dark energy. That is just a term for whatever is causing the second round of accelerated expansion. Beyond that, we have very little idea of what it is. About 23% is made up of dark matter. Now, dark matter acts gravitationally like normal matter, but we have no idea what it is made up of. We do know it cannot be anything in the standard model. Whatever we do know from the standard model makes up a very tiny fraction of the universe today. Crucially, neutrinos form a not negligible fraction of the total energy density. And that is what allows us to use cosmology to measure the neutrino mass. we should keep in mind that this pie chart here is only the energy content of the universe today. At some other redshift, it was the amount of the energy density of the various components were different. So if you look at this plot here, this is the energy density fraction of different components. In this plot, time runs from right to left. So today we are dominated by dark energy, but that kicked in quite late. Before that, the universe was mostly matter dominated, and at high redshifts, it was radiation dominated. Okay? A lot of what we know about cosmology and the cosmological parameters comes from the study of the cosmic microwave background. So this is a map of the temperature fluctuations in the cosmic microwave background coming from the Planck satellite. So this is the CMB surface on the sky. If you look at temperature variations at different points, you get this map. You could analyze this map pixel by pixel. You know, given your cosmological model, you can try fitting this. But it's much easier to think of this as one realization of some underlying power spectrum. So what you do is you take this map, take this spherical harmonic transform, that gives you the coefficients of the various YLMs. Those are the ALMs here. And then you define the power spectrum, or CLs, in this fashion right here. What is plotted here is from the Planck 2018 paper. Instead of CL, they plot DL, but they are essentially the same thing, except factors of L. The red points are the data. The blue line is a 6-parameter fit through this, okay? And it does remarkably well to explain these peaks and troughs and so on. So now, what are the 6 parameters? They're quite physical. One of the parameters is the amount of baryons in the universe. The second parameter has to do with the amount of cold dark matter in the universe. Here, cold dark matter just means something that wasn't coupled to photons at some early time, okay? The third one is the size of the sound horizon at CMB, which is essentially where this first peak lies. That's a very easy observation and a very simple parameter in your model. I'll come to what tau is. AS and NS basically have to do with the amplitude and the shape of the primordial power spectrum. So AS is the amplitude at some fixed scale K0. NS is the spectral tilt. So if you believe in inflation, inflation tells you that the spectrum of perturbations should be almost scale free. So it should almost be k to the 1, but it's not. It's k to the ns, and ns is very close to 1. And this has to do with the end of inflation. Tau is the optical depth. So at some point, once the first stars and galaxies form, the universe is no longer completely neutral. There is an ionized fraction. And so the CMB photons go through this ionized fraction and reach us, which leads to a certain optical depth, which is captured by this parameter tau. Okay, the CMB has taught us a lot of things, but there are things that we do not learn from the study of the primary CMB. And what are those things? So whatever happens to the universe at low redshifts, the primary CMB has no information about that. So for example, the amount of dark energy or its equation of state. This primary CMB cannot tell you that. What is the microscopic nature of dark matter? Is it cold dark matter? Does it have some finite temperature? Is it a WIMP? Is it something else more exotic? Very interesting questions, and I spend most of my current projects on this. And finally, most relevant to this talk is the neutrino mass. The primary CMB itself happens at a time when the neutrinos were relativistic. So there is no information about the neutrino mass on the primary CMB. So to get an answer to all of these questions, you have to understand what's happening at low redshifts, which motivates the study of large-scale structure in the universe. There are multiple other questions which are also investigated through LSS, but these are the ones that I will focus on. Now, the good thing about the CMB is that you can describe everything that's going on in terms of linear perturbation theory. all the temperature contrasts that you have, they're all linear. All the scales that we can measure work perfectly within linear theory. However, as the universe evolves under gravity, the density contrast, which is in the density, that keeps going up. So if you have a region of overdensity, that continues to accrete more material and become more overdense. And underdense part of the universe continues to become more underdense. As this happens, you can define the power spectrum of the density fluctuations in this manner. The same information is also captured in the configuration space correlation function. And as you can see, what happens is that you start off with some power spectrum at CMB, matter power spectrum at CMB, and that continues to grow along with these density fluctuations, okay? Now, the largest scales on this, in this plot, so this is the power spectrum. To the left are the large scales, to the right are the small scales. The largest scales always remain within linear theory. So you can use linear theory to describe these scales. However, on small scales, nonlinearities start developing. You get collapsed objects like halos and so on. And let's see if this works. Here is an animation of what's going on. So it didn't come out very clearly on this, but let's see. So it starts off, so each particle here represents a clump of dark matter. What happens is that you start off with a state that's almost homogeneous initially, and then it collapses under gravity. You form nonlinear structures such as halos here. You also see these completely underdense regions called voids. The collapsed halos are where galaxies form finally, and these come from the peaks in the initial density fluctuations, okay? And the point is that by looking at the clustering of these halos or the clustering of the peaks, you can get information about the clustering of the underlying matter distribution, okay? This is indeed one of the observables of large-scale structure, which is the clustering of galaxies, okay? Photometric surveys basically look at different parts of the sky over and over again, and they just image this, the sky, okay, in different bands. The advantage of this is you get really large sky coverage, but there is a disadvantage, which is that you do not really have redshift information about individual galaxies. You have some very coarse-grained information by combining the different filters, but you don't really have, a good handle on the distances. So what you could do is you can study the clustering of galaxies in different, very broad redshift bins. That's one of the observables that you get from a photometric survey. Now, there are spectroscopic surveys like SDSS, which Ajit talked about yesterday, where you also have spectra for certain galaxies. And in that case, you can actually study the clustering in 3D. This did not render very well on the projector, but this is supposed to be redshift here. So you can, if you look further out, you see galaxies which are much more distant. So this was one of the main observables of large-scale structure, galaxy clustering. The second one, very relevant to photometric surveys, has to do with weak gravitational lensing. So let's say a galaxy very far away from us emits photons. That photon has to travel through the intervening large-scale structure to get to us. And the path of the photon is deflected, especially if it comes close to very massive objects, okay? That is gravitational lensing. So here is an actual image, I think, from the Hubble Space Telescope. And you can see these arcs here. These are gravitationally lensed objects. Now, the efficiency of lensing depends on the distance between the observer and the lens and the source, the observer and the source. But it's a very subtle effect. There are some objects which are stretched out in a way that you know they're gravitationally lensed. But for most objects, the deflection is very, very small. And so it's very difficult to measure. What makes it even more difficult is that galaxies inherently are elliptic. So if galaxies were inherently spherical, then any change from sphericity you could capture as the signal, right? But the galaxies themselves look like this, and then you have small deflections which change their shape somewhat. So if you look at this object here, it originally looked like this. So if someone gives you this image, you don't really know if this object was inherently like this anyway, or this happened through gravitational lensing. So for individual objects, it makes no sense to measure this distortion. This only makes sense once you have many objects, and then you can statistically pull out the signal, okay? That is what weak lensing is. There's also strong gravitational lensing where, for example, this guy is strongly gravitationally lensed because you have multiple images forming. That's roughly the separation between strong lensing and weak lensing. However, since we are surveying large parts of the sky, we do have sufficient numbers of objects for us to be able to pull out this signal, okay? And this is just showing you how this is done in an actual photometric survey. This is from the dark energy survey that's going on currently. This is the probability of a galaxy having a redshift versus redshift. You can see that the redshift bins that you put your lenses and sources into are very broad. Also, it's probabilistic. You don't really know what redshift it is truly at, so your analysis has to fold all of this in. So you have these lenses, you have different lens redshifts, you have different source redshifts. So the lenses sitting here will lens all the sources behind it. So whatever is at a higher Z will be lensed by this bin. This bin will have very few sources behind it, so you won't really see much from it, and so on. So quantitatively, how do you put this together? You have your galaxy positions on the sky in every redshift bin. You can create a map of the overdensities, right? You can take the harmonic transform of that and get the CLs for the galaxy clustering part. You can also take a map of the distortions of the galaxy shapes for the sources, take the spherical harmonic transform of that, and get the CLs for weak lensing. So this is the shear power spectrum. You can also cross-correlate the two maps. What that gives you is the amount of lensing happening due to the galaxies in the lens bin. Okay, that's called CLG kappa. It's not on here. You can also sort of figure out how much noise you will have in all of these measurements. So galaxies are tracers of the underlying dark matter field. However, they are finite in numbers, so they are Poisson limited, Poisson statistics limited, and so you get a Poisson floor on the signal that you have. Similarly, for lensing, what sets the noise is the inherent ellipticity of the galaxy shapes, because then you don't know whether any change came from the original shape or weak lensing. And so that also sets a floor here. You can combine all of these in different ways. So the important point is that all of these CLs, the 2D power spectra that you measure, are some projection of the true three-dimensional power spectrum with different kernels. So if you decide to measure galaxy clustering, that's one kernel. If you decide to measure the lensing, that's another kernel. But all of these are the 3D power spectrum convolved with some kernel, right? So these are the main observables that we'll think about and talk about. I'll move on to the neutrino part, so if you have any questions, just let me know. Okay. So now we move on to massive neutrinos. So measurement of neutrino oscillations have shown us that neutrinos have mass. There are 3 massive eigenstates, but we do know the splittings between them, which is given in this figure here. However, we do not know exactly what the mass scale is, so we do not know what the offset from 0 is. And also, we do not know what the hierarchy is, whether there are 2 heavier species and 1 lighter one, or 1 heavy species and 2 lighter ones, okay? We, of course, know that the neutrino masses are smaller than any other known particle in the standard model. So the mass generation mechanism has been something where active research goes on. There are ongoing terrestrial experiments like Catrin, which are looking to pin down the exact mass scale of neutrinos. But what I'll try to show you is that cosmology actually already places the most stringent bounds on the total neutrino mass. So now let's look at how the energy density of massive neutrinos changes as a function of time. So I go back to this plot over here. The green curve corresponds to neutrinos. So at high redshift, early times, neutrinos are relativistic. So the evolution of their energy density tracks that of photons, which is given in red. At some late time, neutrinos become non-relativistic. So while the photon energy contribution continues to fall, the neutrino energy contribution sort of flattens out, and it starts to act like normal matter. For massive neutrinos, the total energy density at late times is given by this equation here. So omega nu is the energy fraction in neutrinos. That depends on the total mass in neutrinos and some additional factors. So the background evolution of the universe only knows about the total mass of neutrinos, not about the individual masses. It's also useful to define the amount of normal matter that is in neutrinos. This is usually called F nu. So that's energy density in neutrinos divided by the energy density in cold dark matter and baryons plus neutrinos. So you can see that if I fix the amount of dark energy in our universe, increasing the energy density of neutrinos implying decreasing energy density in the CDM, as long as the universe is flat, there's no curvature. Okay? Now let's think about how these neutrinos actually move, or the velocity distribution of neutrinos. At high redshifts, neutrinos, like photons, are coupled to all other particles thermally, and so their distribution is given by a Fermi-Dirac sort of distribution. Once they decouple, what happens is that the distribution that it had just before decoupling gets frozen in, but the momenta redshift as the universe expands. Okay? So that distribution that you had just redshifts. But even when the neutrinos are non-relativistic, they have very large thermal velocities compared to cold dark matter. Okay? And so cold dark matter, you saw the cold dark matter forms different structures. The motion of neutrinos is generally not affected by these perturbations on small scales. On large scales, though, their evolution is affected by gravity. So this is just a cartoon representing that. This is the gravitational potential as a function of x. Cold dark matter produces these perturbations, and cold dark matter sits at the bottoms of these potential wells. Neutrinos, on the meanwhile, they sort of stream about. They don't feel these changes in potential, except for the slowest ones which fall into the potential well. However, these guys cannot escape this large potential, okay? So that's why there is a difference in how neutrinos behave on large scales and on small scales. How do we capture this quantitatively? The starting point is the collisionless Boltzmann equation for each species in expanding spacetime, which I've put down here. This is the distribution function f. P is the momentum, A is the scale factor, E is the energy, and phi and psi are the Newtonian potentials. Now you can take various moments of the collisionless Boltzmann equation to give you something like the fluid equations. So if you take the first moment, that gives you something that looks like the continuity equation, which tells you how the density perturbations evolve with time. If you take the second moment, that tells you how the momentum evolves with time. Now the thing with collisionless fluids, with collisionless fluids is that you can do this, you can continue this process ad infinitum. All you will get is that the time derivative of the nth moment depends on the divergence of the n plus 1th moment, okay? But in linear theory, you just need the first two equations, which is the continuity equation, which depends on the divergence of the bulk momentum, the Euler equation, which says that the change in the momentum depends on the divergence of the stress tensor, the gravitational potential, and because this is happening in an expanding spacetime, there's a Hubble drag term, okay? So let's look at what happens in linear theory. If you drop all terms which are second order in delta or velocity, you are left with this evolution equation. So delta double dot, delta dot depends on the gravitational potential. The right-hand term is the gravitational potential. And then there's a term which depends on the sound speed. For neutrinos, on small scales, the sound speed term dominates. And what happens is that all perturbations on those scales are washed away. Okay? For cold dark matter, it's slightly more subtle. If you look at the right-hand side, it depends on the total matter density contrast. That can be split up into a contribution from cold dark matter and one from neutrinos. I already told you that for the neutrinos on small scales, this term is essentially zero because everything has been damped away. So for cold dark matter, if you compare the evolution of delta in a universe which has massive neutrinos versus one where F nu is zero, there's a deficit on the right-hand side for the massive neutrino universe. And so what happens is that the evolution of the cold dark matter perturbations are also slowed down if you have massive neutrinos. The more energy density you have in neutrinos, the slower the cold dark matter part grows, okay? Now you can also, so I've talked about the cold dark matter and the neutrino over densities individually, but you could also combine them to give you the evolution of the total matter contrast, okay? So if you look at these plots, these are the power spectrum in a universe with massive neutrinos divided by the power spectrum with everything held fixed except for the mass of the neutrinos, which is zero. So the denominator is the cosmology with massless neutrinos. As you increase the mass, the total amount of damping of the power spectrum on small scales increases. So I don't think you can read the labels here. Red has sum of neutrino masses of 0.12, blue has sum of neutrino masses of 0.24, and green is 0.36. So as you increase the mass, this increases. However, on the largest scales, it acts just like cold dark matter, which is what I was trying to show you through this cartoon here. This is the power spectrum of total matter. I can also look at the power spectrum of just the cold dark matter part, which is this dashed line here. And you can see that the amount of damping in the total matter is slightly different from the amount of damping in just the cold dark matter component. In general, if you have some F nu, the amount of total amount of damping that you have in the matter power spectrum is 8 times F nu. But in just the cold dark matter part, it's 6 times F nu, okay? So why am I emphasizing this difference between the total matter part and the cold dark matter part? It turns out to be very important because lensing depends on all the matter distribution, not just on the cold dark matter distribution. But the distribution of galaxies follows just the cold dark matter part. And so then this can be actually used to tell you what the neutrino mass is. If you find differences in the cold dark matter power spectrum versus the total matter power spectrum, that is a sign that you have some other component, in this case neutrinos. Most of our information about neutrino mass comes from the total damping. The total damping, again, depends on the total mass of the neutrinos. However, the shape, how this damping happens, actually has information about individual masses. And I'll come to this toward the end of the talk. Okay. So as I mentioned, weak lensing depends on the total mass. Galaxy clustering depends on CDM component. Unfortunately, there's nothing that we can observe that depends only on the neutrino part. If we could, then that would be the best way to measure neutrino masses. Now let's come to what constraints we can place on the neutrino mass just using scales which are still linear today. And for this, an experiment like LSST, which should be operational in about 5 years from now or so, is very useful. So there's a way of forecasting what constraints you should get for a given experiment through this formalism called the Fisher matrix formalism. So this is basically the Fisher matrix. Let me quickly give you a sort of physical understanding of what's happening. This is the covariance matrix. So the specifications of LSST tell you what noise levels to expect, which allows you to construct this covariance matrix. These terms, these derivatives, tell you how much the observables that you're looking for will change when you change any of the parameters. The parameters are referenced by alpha and beta. So del C, del P alpha, del C, del P beta tell you the changes in CLs when you change the parameters. You sum over all the modes that you expect in your survey, and that gives you the Fisher matrix. So as you can imagine, if these CLs change a lot with a given parameter, your Fisher matrix component for that is larger, and you'll get smaller error bars on that particular observable. The Fisher matrix formalism also allows you to combine constraints from different experiments. So I can combine the constraints that I expect from LSST with what I already know from the Planck experiment, okay? And once you combine all of these things, you can then work out what the constraints on various cosmological parameters is. In this case, we are interested mostly in the sum of neutrinos. So for some context, the constraint on the neutrino mass placed by the Planck experiment is something around 0.25 electron volts for the total mass, okay? For LSST, even if I put every galaxy into just one redshift bin and look at its clustering and the lensing, I will already be able to place constraints of 0.093, okay? That's already a gain of about a factor of 3. However, I can do something better. I can have more redshift bins. This allows you to amplify the signal and also reduce the systematics at the same time. So if I have 4 source bins and 4 lens bins, like here, then I can improve my constraints to 0.052, and you can keep playing this game till you actually saturate, because you don't have very fine-grained redshift information. You can add in information from other experiments. And the bottom line is that just by using scales which are linear in LSST, you can get down to constraints on the neutrino mass of 0.028 electron volts. Now, the minimum mass that's allowed by the oscillation experiments is 0.06 electron volts. So this tells you that you can already measure, in the worst possible scenario, you can already measure this at 2 sigma. If you also include information from the lensing of the CMB, so again, the CMB is also lensed by intervening large-scale structure, you actually get a 3 sigma constraint on the neutrino mass, okay? Now, 3 sigma is good, but it's not good enough. So what people are looking at is to increase the range of scales that you use in your analysis, and for that, you have to push to small scales which are nonlinear. And that gives me a good segue into n-body simulations, which is what people use to compute the complete nonlinear evolution of the matter field. So n-body simulations have been very popular in studying the nonlinear clustering of matter and halos and so on. The essential idea is that you start at some high redshift when the perturbations are linear. You set down particles, and you set down the particles, you choose their positions and velocities in a way that it's consistent with the power spectrum and the growth rate at that high redshift, okay? There's something called the Zeldovich approximation which allows you to do that. Once you've set that up, you let those particles evolve under their gravity, okay? These are the governing equations here. This is the end product of one n-body simulation. This is a cutout from the simulation volume, and you can see a dark matter halo forming at the center. However, one should keep in mind that this n-body formalism depends very strongly on the fact that the number of simulation particles in a given region that you find at any time is a very good approximation of what the true physical density is over there. And for this reason, this is extremely useful for cold dark matter, because the initial state of cold dark matter is extremely ordered. You just have the bulk velocity. You have no thermal randomness. And so you can imagine that if you have neutrinos with these large thermal velocities, this introduces an extra randomness. And this has been a problem with doing full nonlinear simulations of neutrinos for the better part of the last 8 years or so. That's when people actually started doing this. So we actually came up with a method which for the first time could follow the complete nonlinear evolution of neutrinos in these simulations without having these noise effects, okay? And so this is, again, a cutout from one of our simulations. This is the cosmic web structure in the CDM component. You can sort of see halos, voids, and so on. This is the cutout from the same simulation for a massive neutrino of 0.5 eV. And then we ran another simulation with massive neutrino of 3 eV just for fun. This is not allowed by the current constraints anyway. But the major takeaway is that the neutrinos also condense onto this web-like structure that CDM forms. However, the density contrasts are much lower, okay? You still see a lot of neutrinos in these deep voids. You don't see as much enhancement at the most massive clusters and so on. Then last year, we realized that there's an even simpler way of doing this neutrino simulations without noise. All you have to do is you have to choose your initial conditions slightly cleverly. And so this figure here shows 2 simulations run with exactly the same number of CDM and neutrino particles. I'm plotting only the neutrino densities. The right-hand figure is this new method where we chose the initial conditions in a slightly different way. You can actually see the web structure again. You can see overdensities, underdensities, et cetera, in the neutrinos. This had the same number of particles. So naively, you would expect the same noise levels. And it's supposed to be exactly the same field. But you see, this is just noise, okay? And yeah. Very important question. What is this noise due to? As I said, you want the number of particles in a given region to be a good representation of the underlying density. If you have more particles, you can get down to lower density contrast. If you have very few particles, you cannot do that. So this is essentially shot noise. You are Poisson statistics limited. So that's what it comes down to. And that's why I said if you have the same number of particles, you expect the same noise. But that's not true if you have thermal motion. You can choose your initial conditions differently to beat down noise. You can make it very regular. That's the point. Mm-hmm. Yeah. Look very similar. That's exactly the point. On large scales, they do look very similar because for 3 electron volts, the free streaming scale, or the scale at which the neutrinos look different from cold dark matter, is about 100 megaparsec. And that's more or less what your eye can see in this plot. If you actually magnify one of those regions, you'll still see differences. And that's a very important point. The mass of the neutrino tells you the scale at which it should start looking different from CDM. And that is how you actually figure out that it's massive neutrinos and not something else.
But the mass equal to 3 electron volt,
Mm-hmm.
that simulation also includes cold dark matter.
Yes, absolutely, yes.
What is the ratio of
So once you fix the mass, the total mass, that tells you what the total energy in neutrinos is. That also tells you what F nu is, what the fraction of neutrinos to cold dark matter is. The assumption here is that I fix omega lambda, the amount of dark energy. But when you actually do the calculation for measuring the neutrino mass, all of these are free parameters which you will fit to data. But for the simulations, you fix omega lambda, and then you sort of partition the energy between neutrinos and cold dark matter. Right. So the first use that you can put these simulations to is to compute the full nonlinear power spectrum of matter. And so you can see that if you use linear theory, you would get one prediction for the matter power spectrum. Again, I'm plotting the ratio because it just allows you to see things better. But if you do the full nonlinear simulation, you see that on small scales, right-hand side of the plot, you see some differences. You actually see an enhancement of the damping and so on. And this can actually help you constrain the neutrino mass better. okay? But then there are other things that you can, very interesting things to me, that you can do with these simulation, and that has to do with the bias of nonlinear objects. So let me define what bias is. So in this figure here, the blue represents the underlying cold dark matter field. The red represents all collapsed objects. The yellow represents the most massive of these collapsed objects where you can presumably host galaxies. Now, let's say I draw some spheres here, given by the white, which are much larger than the typical sizes of these objects. Inside each sphere, I can compute what the density contrast is. So I find the density within one of these spheres for the blue, subtract the average density of all of these spheres, divide by the average density. I can also play the same game with the yellow points within each of these spheres. So that's delta H, delta halo. So that's the number of yellow points within this sphere minus the average divided by the average. Excuse me. So now I can write down this equation here, which says delta halo is some number b times delta matter. Now, to be, if I'm completely general, each of these spheres should have a different b, or different bias. Similarly, if I wrote this in Fourier space, I would say delta H at some vector k is a bias factor which is specific to that k times delta matter. But that's not very useful. That's not telling me anything. It turns out that if gravity is local and the scales of these white spheres that I drew are much larger than the sizes of these typical objects, I can replace this equation by this. So what is this saying? It's saying that for every sphere, I have the same bias parameter, and if I change the size of the sphere, as long as the sphere itself was much larger than the sizes of the halos, I have the same value of the bias. That is not a trivial statement, okay? And so what, in terms of the power spectrum, what this is saying, so if you take the power spectrum that these densities imply, it says that if this curve in black is my matter power spectrum, this one in red is my halo power spectrum, then on large scales, they look exactly like each other, but boosted by a certain factor, okay? The blue is the cross spectrum. Again, that should look exactly like the black, except boosted by a factor. Okay. It's not an assumption. You can actually prove this rigorously using a spherical collapse model or something like that. What happens is that you can divide up your perturbation into small scale modes and large scale modes. As long as the large scale modes are from a scale which is large enough to be considered a DC mode in your spherical collapse calculation, it doesn't matter what that k was. It just matters what the value of the perturbation was. So that's why one important assumption is that the scales that you're looking at are much larger than the collapsing region. Does that answer your question? We can talk about this later if you're interested. This has been tested very rigorously both through analytic calculations and in simulations. We can actually go ahead and measure this. Now, all of this framework was for a cosmology where you only have cold dark matter. If you also have neutrinos, first of all, the definition of bias is now ambiguous. You can define the bias with respect to either just the cold dark matter component or the total matter component. But there's another interesting effect. What happens is that if you define the bias of the halos with respect to the matter component, you see a small scale dependence on large scales. It's not very significant, but this was discovered in 2014. You expect it to be flat, which is given by these straight lines here, but you end up finding them to be slightly off from the straight lines when you measure them in simulations. It turns out that if you had defined this bias with respect to cold dark matter, on the other hand, you would still get flat lines, okay? So for halos, if you define the bias in a neutrino cosmology with respect to matter, you see some scale dependence. It's not completely flat like this one would have you believe. Then in 2016, we showed that this effect becomes stronger if you look at voids. Why is that? Voids are extremely efficient at throwing out cold dark matter, but neutrinos, because they're thermal, the voids are not as efficient at throwing them out. So within voids, you get an enhancement of the total matter coming from neutrinos as opposed to coming from cold dark matter. So neutrinos are more important in voids than in the more overdense regions. And the other thing that we showed is that the scale dependence is of a very specific type. The scale dependence is actually given by the ratio of the power spectrum of the neutrinos to the power spectrum of cold dark matter, okay? If I had a cosmology with just cold dark matter, I would get this blue line. When I do the same calculation in a cosmology with neutrinos, I get the black and the red. And now that tells you why this is a good way of constraining the neutrino mass. That's because the power spectrum of the neutrinos itself depends on the neutrino mass. And so if you can measure this shape, that tells you what the neutrino mass is. Let me quickly speed through the last few slides. These are very unique signatures of neutrino mass, but the problem is that the signal is very weak. To find this one, for example, you would have to look for voids in the lensing signal. And as I said, the signal to noise in lensing is very low. So it's quite a challenge to actually find this in survey data. So what we are working on right now, this is in prep and should be out within this month, is to somehow use the large-scale environment that these halos or voids live in to enhance the signal. So what do I mean by that? So suppose I have a simulation. I find all the halos in the simulation, find their bias as I defined earlier. I would get this black dotted curve, let's say. Now, for every halo, I can again draw a sphere, find the total cold dark matter density within that sphere, then take those halos which have the maximum overdensities of cold dark matter around it, and the other half has the lower cold dark matter densities around it. So if I draw a circle, a sphere of 10 megaparsec, and I do this exercise, I split it into two halves, all the halos into two halves, find the bias of each of those halves, I would get these two red lines. If I do it at 20 megaparsecs, I would get the blue lines, and so on. But the essential point is that on large scales, the bias is still flat, okay? And that's what we expect. You can work out why this should be that. Now I can play the same game, but instead of the cold dark matter density around every halo, I can find the neutrino density, which I can easily do in the simulation. If I do that, split the halos based on what the value of that enclosed overdensity is, if I do it with the neutrino density and compute the bias, they look completely different, okay? There's this whopping scale difference, scale dependence in the bias on large scales. Again, you can show that this is fit exactly by the ratio of the power spectrum of the neutrinos to cold dark matter. So the lines are actually fits. I have just two free parameters for this entire fit, which is one scale independent number A and one scale independent number B, okay? And that's very important because in general, A and B could also be functions of scale. The important thing is that this effect that I'm showing here is independent of F nu, or the total mass. This just depends on the individual masses, okay? This effect, which is different from the total damping of the matter power spectrum, just to remind you. We also went through the exercise of trying to reproduce this split using observables, which is because I can never measure the actual neutrino overdensity, but I can only measure the cold dark matter density or the total matter density. We came up with a way of splitting these halos using just information about the matter and the cold dark matter parts. And once again, we can produce these whopping scale-dependent bias. But I'm actually cheating here because even in surveys, I can never get the actual underlying cold dark matter field. I can just get the halo field, which is some Poisson statistics limited tracer of the cold dark matter field. And we can show that if you use the actual halo fields, your warping scale dependence goes away, but you can still pull out the signal if you take the ratio. You can still pull out the signal. It is much reduced. Instead of factors of 15 or 20, this is a 10% effect. But remember that F nu, or the energy density in neutrinos, is 1%. So this effect still amplifies the signal by a factor of 10, okay? So this is, again, a very unique signature. You do not expect this in a cold dark matter only cosmology. And the next step that we're looking at is to convert this splitting thing into an actual mass bound, which we can get from LSST or DESI. So since I'm coming to the end of my time, I will summarize. So the study of large-scale structure of the universe can help constrain different cosmological parameters. It can tell us about dark energy, dark matter, and so on. I hope I've convinced you that it is also a very useful tool for trying to constrain the neutrino mass. Using LSST and CMB lensing, we can just use the linear scales to get a 3 sigma constraint. We can push to smaller scales using nonlinear simulations. And then we can also use the scale-dependent bias effect to push even further and get a good constraint on the neutrino mass. And that's it. Thank you. Yeah.
So, Arko, the actual measurement of large-scale structure is, of course, trace out the baryonic density outline. So the voids which we see are the voids where there are no baryonic matter. So that need not necessarily mean that's the void in CDM or neutrino field. So if you want to correlate the simulation with the actual observed universe, how would you actually test whether the baryonic matter follow the...
That's a very, very good question. So these are dark matter only simulations. How am I confident that what I find here, I can translate to whatever observable I'm thinking of? It again boils down to a question of scales. So you can show that the baryonic matter follows dark matter on scales down to roughly maybe 2 or 3 megaparsecs. All the observables that I'm talking about are larger than 10 megaparsec. On those scales, baryonic matter follows cold dark matter perfectly. And so, again, that's one of the systematics we have to be very careful about if we want to push to smaller scales, right? So we do have these simulations, and we claim that, oh, we can push to small scales. That's not completely true. We do have to be careful about the baryonic physics. So there are 2 ways to handle this. One is to have some sort of a semi-analytic model for the baryons. So given the dark matter distribution, can you paint on galaxies? The other one is to actually put in baryons into these simulations. Baryonic simulations are very expensive, and it's very difficult to have these really large 1 gigaparsec simulations that I was running with baryons. So you have to run smaller boxes where there is more systematics coming from sample variance and so on. So it's not a very easy problem, but yes, that's a very big concern. And